L sub naught delta t times W sub naught plus alpha W sub naught delta t H sub naught plus alpha W, not W, H sub naught delta t. And then we can, for each of these terms, or factors actually, we can factor out what are the base units there. So I end up with L sub naught out 1 plus alpha delta t, W sub naught 1 plus alpha delta t, H sub naught 1 plus alpha delta t, and an increasingly fading marker. Rearranging a little bit, that is just L sub naught, W sub naught, H sub naught times 1 plus alpha delta t cubed. Questions up to here?
So is that another formula?
We're not done yet.
Oh.
All right, so I got this binomial here being cubed. So I have my final volume is equal to, well, in essence, my initial volume, V sub 0, times, well, what is, if I got a binomial cubed, what is it? Right, A plus B cubed.
A cubed plus A squared times B, oh, there's a coefficient there. 2, 3.
Bringing back some good memories, I'm sure.
Plus 3B squared, A.
Yeah, I'm gonna write the A first.
That's B squared. Cubed. B cubed.
B cubed, all right. The coefficients, 1, 3, 3, 1, Pascal's triangle, ringing a bell, or one of you at least. 2,
Slack.
Pascal's triangle, Michael. The coefficient, you start with 1, 1's always on the outside, all the ones on the inside is just the sum of them, so 1's on the outside does add up to 2. 1's on the outside does add up to 3, 3, 1, 4, 6, 4, 1, and so on. These are the coefficients. So to the 4th power would be 1a to the 4th plus 4a cubed b plus 6 a squared b squared, and so on. All right, so over here, we're cubing that one, so I have 1 plus 3 times 1 squared times alpha delta t plus 3 times 1 times alpha squared delta t squared plus alpha delta t cubed. That's 4 ways to do that. Well, let's distribute the V sub naught. Well, yeah, let's distribute the V sub naught. There are 2 ways of going about it. And it would have been much better than it all the other way. All right. I'm going to subtract the V sub naught because what we're really concerned with, just like before we were concerned with what is the formula for the change in length, here we're concerned with the change in volume, so I'm just going to subtract V sub naught over. So I get the change in my volume is equal to this. But if we think about it, alpha is something like 10 to the negative sixth. And unless we're dealing with temperature changes of 1,000,000, at which point a lot of things break down, this term right here is going to be small. Matter of fact, alpha is small in and of itself. I mean, that is a small number there. But if I square it, it's even smaller. And if I square it and cube it, it's even smaller. So these terms right here really are insignificant. And what I'm left with is 3 v sub naught alpha delta t. And so if we think about the formula for delta L, being alpha, the initial length times the change in temperature, here we have 3 alpha, the initial volume times the change in temperature. This number right here generally is represented by a beta. And whereas alpha is the coefficient of linear thermal expansion, this is the coefficient of volumetric thermal expansion. And it's, as a general rule, 3 times alpha. Questions to you?
What's that symbol to the left of V0?
That's a beta.
Oh, okay.
L for length. So, well, that doesn't really explain why it's alpha. Beta for bulk. Sort of
Can this be interpolated to area?
is there an area
Like, is
equivalent?
it delta A to V0 or 2
Yeah, it should
V0
be.
alpha
Yeah.
delta T?
Because if this were squared, that would be a 2, a coefficient of 2 there, and that would be a 1, but this would be squared, and that would be insignificant. So you'd end up with 2 v sub naught if we're talking about area. A flat plate that expands more this way than this way.
So we were working on something like fighter jets. Would we use the squared and cubed sections of the formula?
I would think so.
Okay. But generally speaking, it's negligible.
Well, physics textbooks, at least beginning physics textbooks, tend to deal with just length. But just deal with, yeah, tangent and length. And you run across that in bridges that you have, it's built in sections, and then at the end of one section, you sometimes see a grading like that, and then another grading like this. And a support that is much bigger than that. So, but it allows for some expansion during summertime and contraction during wintertime. Because without it, it would bubble, presumably. So going back to our aluminum, this time I've got an aluminum block. Two meters, 3 meters, and 4 meters. Initially at 40 degrees Celsius, it is going to go up to 60 degrees Celsius. And the question is, what will be the new volume? Well, alpha, I know, is 23 times 10 to the negative 6th per Kelvin or degree Celsius, whichever one. strikes your fancy.
I got 0.03312 meters cubed.
You get that?
Yes. Forgot a 3.
That'll do it. So beta is gonna be, doing the fancy math here, 69 times 10 to the -6. So that times 24. Times 20. Presumably, you get that. Patrick, you have a worried look on your face. I'm misreading?
Yeah.
Okay. All right, so I've got, I put energy into it, and because of temperature difference, this thing heats up, it expands a little bit, 0.03 cubic meters, not a heck of a lot. At the same time as putting energy into it, well, I guess it's put energy into it, temperature changes, and therefore the volume for the length changes. But how much energy does it require in order to move it that much? So since we're talking about energy being transferred as a result of thermal differences, so I've got an oven at 60 degrees Celsius. I stick a block that's 40 degrees Celsius into it. Energy goes in, and there's going to be a change in temperature. So, what's missing? Obviously, I left a big gap there. Let's think through it. What's the relationship between, or what is going to affect how much the temperature is going to rise, besides the amount of energy I put into it?
The volume, or the mass?
And there's one other thing.
Specific temperature?
Specific time, specific temperature.
Heat capacity or something like that? Something specific about the materials?
Something specific about the material, specific heat. And that is material dependent.
What does Q represent again?
It represents energy transferred from one object to another because of thermal differences. So, specific heat for aluminum which I did not write down. I did not write down specific heat of aluminum. Can somebody look that up very quickly?
So this is from the block's point of view, of the block.
Yes, the specific heat of the block.
That's, what I'm coming up with is 0.9 joules per gram Kelvin. Is that what you're looking for?
Yeah, let's put it into kilograms there. So that would be 900 joules per kilogram Kelvin. All right, so let's try to figure out how much energy it's going to take in order to do this. Well, how do we find the mass?
Density.
Okay. Density of aluminum, I do remember. Density of aluminum, 2.7 grams per cubic centimeter. But because we're doing traditional stuff and I've got joules per kilogram over the Kelvin over there, let's get this into kilograms per cubic meter. So I want it to be kilograms per cubic meter. What would it be?
2,700.
All right, so I know the density, so let's figure out what the mass is over there. So 27, so I know density is mass divided by volume. So the mass is volume times the density, which is 24 cubic meters times 2,700 kilograms per cubic meter. So more than 500,000 newtons in terms of weight if it were on Earth. So we have this huge amount of mass there because I made that a huge block. So the amount of energy would be 64,800 kilograms times the specific heat of 900 joules per kilogram Kelvin times 20 degrees Kelvin, or sorry, my apologies, 20 Kelvin. My general advice is if you have a 24 cubic meter piece of aluminum, something that weighs more than 500,000 newtons, don't try to heat it up 20 degrees Kelvin, or 20 Kelvin. That's a lot of energy. In terms of weight, let's see, you got weight, so very crudely, 1,000 newtons. So if I divide by 5, so 12,000 pound block. Somewhere around there, I think. No, 120,000 pound block. Or if it's pure aluminum, just let it sit out in air and it will slowly disintegrate.
Why would that be?
The outside oxidizes, create aluminum dioxide, which in its natural state or room temperature state will basically be powder and it will fall apart.
I thought aluminum is one of the most corrosion resistant materials in the world?
Those are actually aluminum alloys.
Oh.
I had a student give me some pure aluminum, which I had sitting on one shelf, and just over time, it was over a couple of years, it wasn't as big as it used to be. Charles Law. Sorry, sort of shifting some gears here. Charles Law. Any of you remember Boyle's Law, Gay-Lussac's Law, Avogadro's Law? Ideal gas law,
Was that PD equals nRT?
that's the one, yep. The other ones, well, not quite, I guess from a historical point of view, the other ones have importance, but it's all, the four laws I mentioned before, ideal gas law, are all bundled up in the ideal gas law. Just a matter of, you hold one of the variables constant, or you hold two variables constant and how the other two react to each other, whether they're directly proportional or inversely proportional. That's the other four laws. So I'm gonna put it up in the corner and we will come back to it. Or, sort of the chemistry version, we also have big N case of D, T. First, let's hit the variables here. P is for, it sounded like you stopped before you finished.
Pressure.
Yes. V.
Volume.
Are we letting Patrick answer all the questions today? Is it's so obvious I'm gonna let someone else do it, or is it, I'm not 100% sure?
The latter.
The latter, okay.